I think there's only 4 questions on the part 2 of the chapter 3 practice test, but they have many parts, so let me just jump into this. 6a gives me a function. It's a polynomial and asks me to find the domain. The domain of any polynomial is negative to positive infinity, and there's no algebra you can do to find the domain. If you did algebra, you're probably going to find the x-intercepts, which I'm about to do in part B. To find the x-intercepts of this function, really, oh well, I'm not that excited about the function, but to find the x-intercepts, I'm going to take the function x cubed minus 3x, set it equal to 0. I'm going to factor out an x and get x times x squared minus 3 equals to 0. I'm going to set the factors equal to 0. I'm going to go x equal to 0 and x squared minus 3 equal to 0. The x equal to 0 gives me one of the x coordinates of the x-intercept without any extra work. The x squared minus 3, to get the x-intercept from it, I'm going to have to add 3 to both sides, and that will give me x squared equals to 3. And then I'm going to square root plus or minus square root and get x equals plus or minus the square root of 3. My answer to 6b is going to be 3 distinct points. And an x-intercept always has a 0 in the y-coordinate. So I'm going to write 0, 0 for that. And then positive square root of 3, 0 for the plus square root of 3. And minus square root of 3, 0 for the minus square root of 3. Ultimately, my goal is going to be to graph this function. So let me start making a graph and put these x-intercepts on the graph. This is going to be part J. And immediately, I don't know what square root of 3 is. So second square root of 3 is 1.73. So on my graph, I'm going to have 3 x-intercepts, and two of them are negative and positive 1.73. So as I start to mark up my x-axis, I'm going to put a couple of the x-intercepts, all 3 of the x-intercepts on my x-axis. I'm going to call this the point negative square root of 3 comma 0. I'm going to call this the point 0, 0, and then maybe there positive square root of 3 comma 0. So I have all 3 x-intercepts shown on my graph, and I'm ultimately going to need to graph everything, so let me just keep this handy. Part C wants me to find the y-intercept. To find the y-intercept, you just plug 0 in for the x. I'm going to go f of 0 equals 0 cubed minus 3 times 0. I know that comes out to 0. My answer to part C, I plugged in 0 for x, and that's the y part of the y-intercept, and I got 0 for y. I don't need to show that point again on my graph because I already have it. Now I need to find where the graph is increasing and decreasing in the maximums and the minimums, and I'm going to do that on the bottom of the screen. I'm going to find the first derivative. So I'm going to go f prime of x equals the derivative of x cubed is 3x squared. The derivative of minus 3x is minus 3. I'm going to get critical numbers by taking that derivative and setting it equal to 0. I'm going to go 3x squared minus 3 equals to 0. I'm going to be lazy. I have a problem that has an equal sign and a common factor that doesn't have a letter. Instead of factoring out that common factor, I'm going to divide that common factor away. That's going to leave me with x squared minus 1 equals to 0. I'm going to factor that into x plus 1 times x minus 1. I'm going to set the x plus 1 equal to 0 and the x minus 1 equal to 0 and get critical values of x equal to negative 1 and x equal to positive 1. Once I have the critical values for the first derivative, on a number line I put negative infinity, positive infinity on the edges. I put the critical numbers between the infinities, and then I create intervals with all round brackets. I'm going to do an interval from negative infinity to negative 1, an interval from negative 1 to 1, an interval from 1 to infinity, and then in each interval I pick a test number and plug that test number into the first derivative. The first interval I'm going to pick x equal -2 because -2 is inside that interval. The middle interval has 0 in it. I'm going to pick 0. The far interval has 2 in it. I'm going to pick 2. And I'm going to find f prime of -2. I'm going to find f prime of 0. And I'm going to find f prime of 2. And I'm going to get lazy and use the dy dx feature on my calculator. So to get this part answered, I'm going to, into my y1, put the original function, x cubed minus 3x, and I can graph it. Ultimately, I'm going to have to reproduce that graph on my graph, but for now, I'm going to do the increasing and decreasing part. First, I'm going to do f prime of -2 by going second calc, option 6 dy dx, type in the number -2 and hit enter, and it tells me that I get, I think, +9. I'll round that. Next number I'm going to do is 0, second calc, dy dx, type in 0 and hit equals, and I'm going to round that to -3. And then do the same with +2, second calc, dy dx, type +2, hit enter, and I think you get +9. So now I can figure out where the graph is increasing and decreasing. In the first interval, because I got a positive, the graph is increasing, and that's going to go into my answer for part D. It's increasing from -infinity to -1. The next interval, when I plugged in 0, I got -3. That makes a decreasing interval. I'm going to put that interval from -1 to 1 in my part E. In the last interval, from 1 to infinity, I got a +9. Since I got a positive number, I get an increasing interval. I'm going to put that interval in part D. I'm going to separate these with unions. And now I'm going to figure out where I get the maximums and mins. The first interval, the graph is going up. The middle interval is going down. In the last interval, it's going up. So now I can see there's going to be a relative maximum, and its x coordinate is -1, and there's going to be a relative minimum, and its x coordinate is +1. I'm going to get lazy and not break up the maximum and the minimum because it's going to take too much time. So as I go to answer part F, I'm going to say there's a relative maximum, and the x coordinate is -1. I'll need to do some work to get the y coordinate. And I'm going to say there's a relative minimum, and the x coordinate is 1. And I'm going to do some work to get the y coordinate. Because this is such a nice function, I can cheat to get the y coordinates by using the table on my calculator. So let me just sneak at the table by going second table. The table shows y coordinates next to x coordinates. So the y coordinate next to -1 is y equal -2. That's going to finish up my relative maximum. And the y coordinate next to +1 is -2. That's going to finish up my relative minimum. Done with part F. I have 2 more points to plug on my graph. So I'm going to plug the point -1, +2, and +1, -2 on my graph. So my graph now, my y-axis, I need to start marking it up because I need some more depth to this graph. I'm going to put the point -1, +2, which is the relative maximum point, and the point +1, -2, which is a relative minimum point. Not going to sketch any graph yet until I get done with all the parts, but I have already 5 points on my graph. So done with part F, moving on to part G and H and I, which are the concavity parts. For G, H, and I, to figure out where the graph is concave up, concave down, and where the inflection points are, I need to have some work with the second derivative. So I'm going to do my work for G, H, and I on the bottom of this page. So the function is x cubed minus 3x. The first derivative was 3x squared minus 3. The second derivative is just going to be 6x, and just 6x because that 3 is a derivative of 0. When I'm working with concave up, concave down, or concave upward, concave downward. I take the second derivative, set it equal to 0, and solve for x to get my critical value. The second derivative is just 6x. When I set it equal to 0, I get x equal to 0. I'm going to put on a number line, negative infinity on the far left edge, positive infinity on the far right edge, 0 between the infinities, which is my critical value. Create an interval from negative infinity to 0, an interval from 0 to infinity. Now I'm going to plug test numbers into the second derivative. First interval, I'm going to pick -1. Second interval, I'm going to put +1. I can't really do this on my calculator, but it's not so hard to do. For second derivative evaluated at -1, I do 6 times -1, which is -6. For the second derivative evaluated at +1, I just plug in a 1 for that x. I get 6 times +1, which is +6. The first interval is going to be concave down, or concave downward, because I got a negative when I plug that number into the second derivative. The second interval is going to be concave up, because I got positive when I plug that number into the second derivative. So now I can answer part G. The graph is concave up, or concave upward, in the interval from 0 to infinity. It's concave down, or concave downward, in the interval from negative infinity to 0. And this right here, because the graph is changing concavity, is going to give me an inflection point. The x-coordinate of the inflection point is 0. To get the y-coordinate of the inflection point, I need to plug that 0 into the original function. Or I can cheat and look at my table, because my table has y-coordinates for x-coordinates. And next to x equal to 0, I see y equal to 0. The y-coordinate of the inflection point is 0. This would be another point to plug on my graph if I didn't already have it there. So I have all the points. I have this relative maximum. I have a relative minimum. I have 3 x-intercepts. One of them is an inflection point and also a y-intercept. So now I have a perfect setup for my graph. I'm just going to borrow the graph from my calculator. I just entered the function. I did a zoom standard. And I'm going to borrow and just kind of sketch a graph that looks like the picture here. So the graph between the beginning of the graph, which is negative infinity, up to it goes through the x-intercept where it's increasing and concave down. It continues going up, up, up. It's concave down and increasing all the way to the relative maximum. And then at the relative maximum, it starts decreasing but stays concave down. So my graph is concave down, and decreasing, concave down, and decreasing. Once it gets to the inflection point, the graph is going to flip over in terms of concavity, but it's going to stay decreasing. So increasing concave down, decreasing concave down, and now decreasing concave up. It gets to the minimum point. It stays concave up. It stays increasing, but concave up for the rest of the way. When I look at my graph on my calculator and I look at this graph, they look kind of close to each other. I feel good enough about the graph. It does everything it needs to do. It increases where it needs to increase. It decreases where it needs to decrease. It's concave down first, concave up second. It has the right maximums and minimum points. That's completely an accurate answer for part J. And that would be the end of problem 6. So that took me 14 minutes to do. This test is definitely going to be a slow test because graphing just is a very slow process. So now I'm going to do the same sort of thing for the function 2x e to the x. This function doesn't have anything to restrict the domain. The 2x and e to the x are defined everywhere. There aren't any fractions to make any asymptotes. So the domain for this is still going to be negative to positive infinity. To find the x-intercept, I'm going to take the function and set it equal to 0. This function's already factored, so I'm just going to split the factors up and set each factor equal to 0. The factor of 2x if I divide both sides by 2, I get the x-coordinate of an x-intercept at 0. And the e to the x can't be 0. So I have the x-coordinate of my x-intercept, which is x equal to 0, and the y-coordinate of every x-intercept is 0. In a minute, I'm going to plot that on the graph, but let me get C done before I flip onto a new sheet of paper. To find the y-intercept for part C, I plug in 0 for all the x's. I get f of 0 is 2 times 0 times e to the 0. E to the 0 is 1, so this is 2 times 0 times 1, and that's equal to 0. The y part of my y-intercept is 0. The x part of any y-intercept is always 0. So both the x and the y-intercept are 0. Let me start off with my graph now. And this is going to be part J of number 7. I'm going to plot the point 0, 0, which is simultaneously both an x and a y-intercept. Now I'm going to work on the increasing and decreasing part of this, and to do that, I need to do the derivatives. So I have the original function, f of x equals 2x e to the x. I need to find its first derivative, so I'm going to use the product rule. I'm going to take 2x, multiply it by the derivative of e to the x, and then I'm going to take e to the x and multiply it by the derivative of 2x. This is going to give me 2x e to the x, because the derivative of e to the x is e to the x, plus e to the x times 2, because the derivative of 2x is 2. I'm going to factor out a 2e to the x, and when I factor out a 2e to the x, I take that away, that away, that away, and that away. To the left of this plus sign, inside of parentheses, I'm left with an x. To the right of the plus sign, because I've taken out the entire factor, I'll be left with a 1. I'm going to get my critical values by taking the 2e to the x and set it equal to 0, and I'm going to set the x plus 1 equal to 0. The 2e to the x can't ever be 0, and when you set the x plus 1 equal to 0, you minus 1 from both sides, and you get x equal to minus 1. The only critical number for the first derivative is minus 1. And so to do the increasing and decreasing part, I'm going to create a number line that has the infinities at the edges, -1 between them. I'm going to create intervals from negative infinity to -1 and -1 to infinity. In each interval, I'm going to pick a number to test into the first derivative. In the first interval, I'm going to pick x equal -2. And in the middle interval, second interval, I'm going to pick 0, but I could have picked x equal to +2 if I cared to, but 0's in that interval, I like checking it. First interval, I need to do f prime of -2, which I'm going to get a decimal for on my calculator using the dy dx feature. Second interval, I need to do f prime of 0. Again, I'm going to do my calculator and get a decimal answer. So into my y equals, I need to put the function 2x e to the x, and now I'm going to graph it. I might have to work on this window, but I'll live with it for now. I'm going to go second calc to find f prime of -2. I go down to dy dx, I type in -2 and hit enter, and I get -0.27. And then for f prime of 0, second calc, go down to dy dx, type in 0, and I get +2. So first interval, because I got a negative, the graph is decreasing. Second interval, because I got a positive, the graph is increasing. So the graph does something like this. It decreases, and then it increases. I can write my answer to part D and E. For D, it's increasing from -1 to positive infinity. I can write my answer to part E. It's decreasing from negative infinity to -1. I'm going to give a lazy answer for part F and just give the coordinates. And these arrows tell me that I have a relative minimum at x equal to -1, and I don't see anything that gives me a relative maximum. So when I go to answer part F, for the relative maximum, there's going to be none. The graph only changes direction once, and it gives me a minimum there. And for a relative minimum, I'm going to take the x-coordinate of -1, and I'm going to by hand get the y-coordinate. The reason by hand is my calculator is going to give me a decimal. I'm going to plug -1 in for this to get my y-coordinate. I'm going to go f of -1 equals 2 times -1 times e to the -1. That's going to be -2 e to the -1, and that's the same as -2 over positive e. So that's going to be -2 over e. I'd like to plot that point on my calculator, or on my graph. I'm not really sure where that is. So I'm going to get a decimal equivalent for that point by going second table, looking next to -2, and that's -0.54. So on my graph, I'm about to plot the point -2, -0.54, and I'm going to call it, on my graph, I need to do -1. I don't know why I got -2 in my head. I need to plot the point -1, -0.74, which is that point right there. And the best I can now, on my x-axis, I'm going to mark up a -1. And my y-axis, I'm going to mark up a -1. And this is going to point -1, -0.74. So this is going to be my point -1, comma, -2 over e. That's going to be my minimum point. So that's everything from this page. I'm going to move on to the second page and start working with concavity. In order to work with concavity, I have to know the derivative. I actually need to know the second derivative. The original function was 2x e to the x. It's going to probably be easier to use this version of the first derivative to find the second derivative. So I'm going to say the first derivative is 2x e to the x, and that piece I'm going to call it 2e to the x. So in order to work with concavity, I need to find the second derivative, and there's where I'm going for parts g, h, and I. So let me work on this second derivative. To do the second derivative, for this piece I need to use the product rule. I'm going to say it's going to be 2x times the derivative of e to the x plus e to the x times the derivative of 2x. And then the derivative of that piece is real easy. The derivative of any e times a constant without an x is just that function times the derivative of the exponent. The exponent has a derivative of 1, so that piece has a derivative of 2e to the x. So finish this up here. This 2x is going to stay. The derivative of e to the x is e to the x. And then I have e to the x, and then the derivative of 2x is 2. So this is going to be e to the x times 2 plus 2e to the x. This is going to give me 2x e to the x plus 2e to the x plus 2e to the x. I'm going to add those and get 4e to the x. So I'm going to get f double prime of x equals 2x e to the x plus 4e to the x. This, I'm going to factor out a common factor of a 2e to the x. So I'm going to factor out a 2 and an e to the x. I'm out of the bottom of my paper, so I'm going to try to work on this here. When I factor out a 2 and an e to the x, from the first piece I'm left with just an x. And from the second piece, I factored out that e to the x, and that 4 is going to turn into a 2. So I believe the second derivative is 2e to the x times x plus 2, and that's the nicest form of the second derivative. That's what I'm going to use to find out the answers to g, h, and I. So now that I have a really working version of the second derivative, I need to get the critical numbers. And I get the critical numbers by taking that second derivative and setting it equal to 0. So I'm going to take the 2e to the x times x plus 2, and I'm going to set it equal to 0. That's factored, so I'll just take the factors 2e to the x and set it equal to 0, and x plus 2 and set it equal to 0. The 2e to the x can never be 0, so I'm going to write no solution for that. And the x plus 2, I'll minus 2 from both sides and get x equal to -2 for my critical number. I have my critical number, and I have the second derivative. The second derivative is f double prime of x equals 2e to the x times x plus 2. I now need to work on my number line. I'm going to put on my number line negative infinity, positive infinity, put the negative 2 between them, create an interval from negative infinity to negative 2, an interval from negative 2 to infinity. For each interval, I need to pick a number. First interval, I'm going to pick x equal to negative 3. Second interval, I like 0 because it's in that interval. I'm going to plug those numbers into the second derivative. So I'm going to go f double prime of negative 3, which is going to be 2 times e to the negative 3 times negative 3 plus 2. And then I'm going to do f double prime of 0. F double prime of 0 is going to be 2 times e to the 0 times 0 plus 2. I don't care exactly what these equal to, I just care whether they're positive or negative. I'm going to do these on the main screen of my calculator. I'm going to go 2 second ln negative 3 for 2e to the negative 3 times negative 3 plus 2. And I get negative 0.09957. I don't care to round that right now. It's negative, so the graph is concave down. Second interval, I'm going to go 2 second ln e to the 0 times 0 plus 2, and I get 4. So much nicer number. So I know that in the first interval, because I got a negative, the graph is concave down. In the second interval, because I got a positive, the graph is concave up. And the x-coordinate of an inflection point is at x equal to negative 2 because the graph changes concavity. I'm going to get an inflection point there. And before I go back to my other sheet and write all the answers down, let me find the inflection point. The x-coordinate of the inflection point is negative 2. In order to do an inflection point, I need to have the original function, and I can't even find the original function. Here. The original function is 2x e to the x. What I'm going to do in the function f of x equals 2x e to the x is I'm going to plug in negative 2 and get 2 times negative 2 e to the negative 2. That's going to give me f of negative 2 equals negative 4 e to the negative 2. And that's going to give me f of negative 2 equals negative 4 over e squared. That's going to be the y-coordinate of the inflection point that I'm going to write for my answer. It's not going to help me graph, but I'm going to use it here to write some answers. So real quickly now, I need to say where the graph is concave up. The graph is concave up in the interval from negative 2 to infinity. There's my answer to part G. Part H wants to know where the graph is concave down. That's the interval from negative infinity to negative 2. Part F wants the inflection point, and the inflection point is going to be negative 2 comma negative 4 over e squared. When I get a point, I like to graph those points, so I need to graph this point on my graph, and let me figure out where that y is. That y is about negative 0.5413. So when I graph this, I'm going to put it at negative 0.54 in some sense. So let me go ahead and try to graph this point on the graph that I've been creating. So on my graph, I need to attempt to plot that point. So I'm going to go to negative 2, and then negative 0.54, this right here was like negative 0.7. This is going to be a little bit higher. So I'm going to call this point right here the point negative 2, negative 4 over e squared. That's about halfway down. So that's all the points I can have for this. Now I'm going to sketch a graph. On the test, I'm going to give you a blank graph that has the x and the y-axis marked up so you know what a decent window should be. I didn't do that for this problem, so I'm going to figure it out myself what a decent window might be. A decent window is going to be something that really shows these points well. When I look at the points that I have drawn, I see negative 2, negative 1, 0, and I don't see really large x values. I bet you if I just go from -5 to 5 on my x's, that's far enough away from these points that I'm going to see a very complete graph. There's not going to be much interesting going on in the graph to the left of -5 or after +5. And for my y's are all condensed around in between 0 and -1. Let me make my y's maybe go from -2 to 2. I don't think there's going to be anything really interesting going on outside that interval. So now I'm going to graph my function with this window and try to copy it. So there's the function that's in. I'm changing my window. Again, on the test, I'm going to tell you what window to use so you won't have to think about it like I just thought about it. I'm going to hit my graph button, and I'm going to attempt to draw the graph and talk through it. In the beginning, the graph is, apparently it has a horizontal asymptote at the y-axis. The graph is decreasing and it's concave down. It gets to the inflection point where it continues to decrease but becomes concave up. So right here is the inflection point. The graph flips over from concave down to concave up. You can see there's decreasing, concave down, flips over, decreasing and concave up. It gets to the minimum point where it stays concave up and it increases the rest of the way. It goes through the intercept and it's increasing and concave up the whole way. The best I can, I'm duplicating my calculator's graph. Mine isn't like a stellar approximation of my calculator's work, but it's good enough. So the graph from -infinity to -1 decreases, from -1 to infinity increases, from -infinity to -2 is concave down, from -2 to infinity is concave up, has the proper inflection point, has the proper minimum point. That's as decent as I can do for a graph for this function. All right, one last problem, and I think it's not quite as bad. I mean, there's a lot going on, but it's a little bit easier. So the last problem has us do the graph of a fraction, and on the test, I'm going to give you the first and the second derivative for the fraction, so kind of shut the screen down and calculated those derivatives. So on the last problem on the test where we start doing this work with a fraction, you don't have to worry about finding the first and the second derivative. If you do the derivative wrong, then all your work is going to be wrong. So for part 8a, for this fraction to find the domain, I'm going to set the denominator equal to 0. That's going to give me x equal to -3. That gives me the number to exclude from my domain. One way to figure out a nice way to write the domain is to kind of do like we've been doing for the increasing and decreasing. Create a number line that has the infinities on it, the number I'm excluding from the domain between those, and one completely acceptable way to say the domain of this function, part of the answer to part A, I can say the domain is the interval from -infinity to -3 union the interval from -3 to infinity. If you don't like that, you can say the domain is all real numbers except x equal to -3, or just accept -3. So this would be fine for the domain. That would be fine for the domain. The other part of this, it wants the vertical asymptote. This is the equation of the vertical asymptote. So the vertical asymptote is going to be at x equal to -3. I don't know how readable that is. So the vertical asymptote is x equal to -3. So that's everything for part A. I have something to show on a graph. So I'm going to pull out my part where I'm going to do a graph, which apparently is part K for this. And the first thing I'm going to show is a vertical asymptote, which I generally draw with a dashed vertical line that goes through that point. So I'm going to draw a vertical line that goes through -3. I feel like I've made this graph too far to the right. Let me too far to the left. Let me change that real quickly. Make it more centered so I have room to the left of the vertical asymptote to show some work. So let me, how about this? -1, -2, -3, -4. So this is going to be 8 part K. And my vertical asymptote, is this a dashed vertical line that goes through -3? I'm going to just say this right here is my vertical asymptote at x equal to -3. Part B wants me to find the x-intercepts. Technically, I'm supposed to take the whole function and set it equal to 0. Realistically, it's enough just to set the numerator equal to 0. So I'm going to take the function, I'm going to set it equal to 0. I'm going to solve it by cross-multiplying, by making the function equal to 0 over 1, because 0 over 1 is still equal to 0. And then I can cross-multiply. When I cross-multiply down, I get 1 times x minus 2. When I cross-multiply up, I get 0 times x plus 3. This simplifies on the left side the x minus 2, and on the right side 0 times anything is 0. If I just would have set the numerator equal to 0, I would have got here a lot quicker. This gives me x equal to 2, and my answer for my x-intercept is going to be the 0.20. The x part of the x-intercept is what the algebra gives you. The y part of any x-intercept is always 0. That gives me another point to show on my graph. So real quickly, I'm going to go to my graph and plot the 0.20. For the y-intercept, it's going to be a fraction. I just plug 0 in for x, and that's what part C wants me to do. So I'm going to do f of 0 equals 0 minus 2 over 0 plus 3. That gives me -2/3. When I go to answer this for the y-intercept, the y part of the y-intercept is at -2/3. The x part of every y-intercept is 0. Always the opposite letter is 0. So for the y-intercept, the opposite letter is x. The x is going to be 0. I'm going to show that point on my graph. It's on the y-axis, and it's down a little bit, but not down too far. So here's my point, 0, -2/3, the best I can. Finding the horizontal asymptotes, I need to take the limit as x goes to infinity. So do the limit as x goes to infinity of x minus 2 over x plus 3. I'm going to multiply everything by 1 over x. That's going to give me the limit as x goes to infinity. This first piece is going to, the x's are going to cancel, you're going to get a 1. The second piece, you're going to get minus 2 over x. In the denominator, the first fraction cancels, you're left with a 1. And then I get a 3 over x. Now I can plug infinities in and get 1 minus 2 over infinity over 1 plus 3 over infinity. The fractions with infinities in the denominator are equal to 0. So this is going to be 1 minus 0 over 1 plus 0. That whole thing is going to equal to 1. My answer to part D for a horizontal asymptote, the number that it equals to is 1. In horizontal asymptotes, because they're horizontal lines, are y equals, whereas vertical asymptotes are x equals. So y equal to 1 is my horizontal asymptote. That's another feature I can show on this graph. So I'm going to pull out my graph. I'm going to put 1 on the y-axis. I'm going to draw my horizontal asymptote, drawing a horizontal line that goes through 1 on the y-axis. I'm going to say I have a horizontal asymptote of y equal to 1. For parts E, F, and G, which are the increasing, decreasing, maximum, and minimum parts of this, I'm going to use this derivative, which is 5 over x plus 3 cubed, and find the critical numbers. The critical numbers for a fraction you get by setting the numerator equal to 0 and the denominator equal to 0. Setting the numerator equal to 0, because there's not an x, you don't get a solution. There's no critical number there. Setting the denominator equal to 0, I can write this without the exponent, and that gives me 2 factors of x plus 3. If something is factored and set equal to 0, you just set each of the factors equal to 0. Each one of these factors gives me the same critical number of x equal to -3. So now on a number line, I'm going to put my infinities, negative infinity and positive infinity, along with the critical number -3, and I'm going to create intervals, an interval from negative infinity to -3, an interval from -3 to infinity. I'm going to do test numbers. In the first interval, I'm going to test x equal to -4. Because 0 is in the second interval, I'm going to do x equal to 0 for my test number. I'm going to find f prime of -4 and f prime of 0, and I'm not going to cheat, but I kind of cheat. I'm going to be lazy. I'm going to get this using the dy dx feature on my calculator. So on my calculator, I'm going to enter the function x minus 2 divided by x plus 3. I'm going to graph it. I don't care so much what the graph looks like right this second. I'll work on the window in a little bit. But I do care what f prime of -4 is, so I'm going to do second calc value, go down to number 6, type in -4, and I get +5, rounded anyways, and then second calc dy dx, type in 0, and I get 0.55. So that's going to help me answer the increasing, decreasing, maximum, and minimum part. In the first interval, because I got a positive value, the graph is increasing. In the second interval, because I got a positive value, the graph is increasing. So my arrows might look like this, increasing, increasing. So I can now start answering some questions. Where the graph is increasing is both of these intervals, so the answer to part E, it's increasing from negative infinity to -3, and then again from -3 to infinity. For part F, it wants to know where the graph is decreasing. Well, it's never decreasing because I didn't get any minuses when I did this computation. And then part G wants the maximums and minimums. Well, I don't get a maximum or minimum because I need the graph to change directions, and it never changes directions, so there's going to be none for the maximums and minimums. That's everything for E, F, and G. I'll move on to H. Again, on the fraction problem on the test, I'm going to give you both the first and the second derivative because they're kind of monstrous to compute, and if you get the derivative wrong, then all of a sudden everything is bad after that. I didn't pick up any more points to graph, so I'm not going to plot any points. And I'm going to go on to do the concavity work. For the concavity work, I give you the second derivative. We need to get critical numbers. So I'm going to go down the bottom here and try to squeeze this in. To get the critical numbers, I set the numerator equal to 0 and the denominator equal to 0. This derivative needs to have a cube here. Not that that probably matters that much, but it wasn't quite right. So I'm going to set the numerator equal to 0. I'm going to set the denominator equal to 0. For the numerator, because there's no x, there's no solution to that equation. For the denominator, I can write it without the exponent, and then set each of the factors equal to 0. And they all give me the same critical number, x equal to -3. So I'm going to create a number line that has negative infinity on the far left edge, positive infinity on the far right edge, -3 between them, create an interval from negative infinity to -3, an interval from -3 to infinity, and then in each interval I need to pick a number and plug it into the second derivative. In the first interval, I'm going to pick x equal to -4. In the second interval, I'm going to pick x equal to 0. I need to find f double prime of -4, and I need to find f double prime, or the second derivative, evaluated at 0. To do f double prime of -4, let me just do it up here. F double prime of -4 is going to be -10 over -4 plus 3 cubed. Let me just figure out what that is on the main screen of my calculator. So I'm going to do negative 10 divided by parentheses negative 4 plus 3 up arrow cubed, and I get positive 10 for that. And I'll do the same thing for f double prime of 0. So I'm going to do f double prime of 0 is going to be negative 10 over 0 plus 3 cubed. So I'm going to go negative 10 divided by parentheses 0 plus 3 cubed, and I get negative 0.37. So I can start talking about concave up and concave down. In the first interval, from negative infinity to negative 3, I got a positive value, so the graph is concave up or upward. In the second interval, I got a negative value, so the graph is concave down or downwards. I'd like to say there's an inflection point at x equal to negative 3, but that's not a point that's part of the domain. That's actually an asymptote. You can't have an inflection point across an asymptote. There's not going to be an inflection point because of that asymptote. So as I go to answer parts H, where the graph is concave up, it's going to be the interval from negative infinity to negative 3. J, where the graph is concave down, is going to be the interval from negative 3 to infinity. And for the inflection point, if I tried to plug negative 3 into the original function, I'd plug negative 3 into the original function. You'd get a 0 in the denominator, which is undefined. The graph doesn't exist. The function isn't defined at negative 3. So even though it changes from concave up to concave down, it doesn't on either side of an asymptote. And that gives you no inflection points. Unfortunately, all this work didn't give me anything else to really add to the graph, which is really unfortunate because now I'm sitting at a graph that doesn't have so many numbers on it, and I need to get some numbers. And so I'm going to have to play a little bit. My guess is that I need to get past, this asymptote a little bit. I'm going to make my x min negative 10 to get far enough to the left of that asymptote. I like symmetry, so I'm going to make my x max positive 10. And I'm not really sure where the y should be. Usually before I write a test and I draw the blank graph for you, I play on my calculator a little bit to see the y's. I've graphed a lot of fractions before. My guess is if I don't get quite high enough, I'm not going to see two sides to the graph. There should be a graph over here and a graph over here. And if I don't make my y's high enough, I might not see them. Let me do negative 10 to 10. And if I think I can see everything I need to see, I'm going to leave that window. If I can't, I'm going to tweak the window. So I have the function in already. I'm going to do a zoom standard or make my window negative 10, negative 10 to 10 on the x's, and negative 10 to 10 on the y's, and just cross my finger that I can see everything that I want to see. If I don't, I'm going to change the y min and y max. I can see everything I want to see, but I don't see the vertical asymptote. I don't see the horizontal asymptote. I love having those in there. Let me get them one at a time. Let me do the horizontal asymptote of y equal to 1 because that's easier. Into y2, I'm going to type the number 1. And now hit graph. Now I can see my horizontal asymptote just fine. Don't see my vertical asymptote at x equal to negative 3. To get the vertical asymptote to show up, you need to take the denominator and multiply it by 1,000 to get something that looks like a vertical asymptote. The vertical asymptote's not a function. Technically, my calculator doesn't know how to draw it. But I can cheat, take the denominator, which was x plus 3, and multiply it by 1,000. And that's going to look like my vertical asymptote. Now I'm going to hit my graph. There's my vertical asymptote, and let me sketch this graph. So in this first region, the graph is increasing and concave up. If I looked at my little work, it says between negative infinity and negative 3, it's increasing and it's concave up. And there's a picture of a graph that's both increasing and concave up. In the next interval from negative 3 to infinity, the graph is increasing and concave down. It also has to go through both the x and the y-intercept. So in this region here, I'm going to make my graph increasing and concave down. So there's increasing, concave down. It goes through the x-intercept, it goes through the y-intercept, and then it gets drawn to this asymptote. and that looks enough like this graph. It goes through the points it needs to go through. I'm going to call that good enough, and I'll be done with this entire review. So this is bound to be a long test because these problems take so long to do. I generally get to class early. In fact, I have a class that I think ends at 9:30. Usually if your class starts at 10, feel free to get to class as close to 9:40 if your class starts at 10 to get started on this if you're a slow test taker and you need some time.